All right, great. So I guess I'm up next, and so I'm Todd Coleman. I'm at UC San Diego, the Department of Bioengineering. Before that, I was at University of Illinois, Urbana-Champaign. And so I'll be talking about interactive information theory and brain-machine interfaces. And so I guess where I start is to sort of explain what I mean by brain-machine interface. And what I mean is any type of device that elicits a direct communication pathway between the brain and an external device. And so traditionally when people were developing brain-machine interfaces, they were primarily interested in helping people to recover from the loss of some type of deficit. For example, if you think about a cochlear implant that takes sound information and stimulates neurons on your auditory nerve, or if you've heard about retinal implants that do analogous things, or if you hear about motor output systems, where maybe a soldier comes back from the war and maybe he's paralyzed, but if you can put electrodes right onto his motor cortex, you can decode those brain signals to possibly operate a robotic arm. So these were sort of the traditional sort of applications that people thought about for brain-machine interfaces, but in the last maybe 5 or 10 years, the field has really begun to expand to explore applications beyond simply helping people with deficits. And for example, there's a company based in New York that's developed an application where in certain situations for searching for certain types of image of interest, by directly acquiring brain signals rather than relying upon you hitting the next button, you can speed up search by a factor 3. Okay, in other situations, you might have heard of Emotive or NeuroSky. These are companies that are building little gaming applications, and there's a company right down the street here that's trying to use this for marketing, and also the Department of Defense is using a lot of these technologies for a variety of brain fingerprinting ideas. It's harder to lie when I'm directly picking up your brain signals. So the punchline is we can really imagine where the future is going to lie, especially in the Pardon me?
We are going to be less active in the future.
Depends on how you look at it. Yeah. So, so now perhaps I can tell you about when I entered the field maybe 6 years ago, the way we were taking a look at a lot of these problems. So the way a lot of people thought about these problems involves you have some human, and maybe he's imagining some command, or there's some internal brain state, which we'll call this little X right here. And then what's going to happen is they're going to imagine some command, and then you're going to acquire some neural signals. So in this scenario, we've got this guy Ray here, some 3 people in the audience know, and he's got this brainwave EGCAP on his head. So you record all these different waveforms, and so this is sort of in some sense a noisy reflection of the imagined command because the statistics of these signals change depending upon what command you're imagining. And then from that, the system, does a little bit of statistical analysis, and it says, what was the likelihood he imagined left, or what was the likelihood he imagined right, and maybe moves a ball on the street, or something like that. So I thought some of you might care a little bit about, well, how is this noisy channel modeled? So I'll just spend a little bit of time going into this. And so, what sort of an example, so we can imagine here that X is binary. Either I imagine squeezing my left hand, or I imagine squeezing my right hand, and I'll record 80 EEG signals. And so if you remember that cap, these electrodes are placed in different areas on the head, okay? And so what I'm acquiring are these voltages in different parts of the surface of the head. And what we can imagine is because of the biophysics and the brain tissue in the skull, there's some type of, you can imagine that we have a bunch of little sources right here, which are these yellow guys. And each source, there's sort of EMAG wave propagation that's hitting all of these electrodes. And how much hits this one versus this one depends upon the distance and the laws of physics and the absorption of the brain, et cetera, et cetera. So it's basically biophysics that can tell you about what this matrix is, which is the linear operation going from these yellow guys to these black guys. Obviously, we have observation noise also. Then on top of that, what is the source of those yellow guys, those Ds? Well, we take into consideration what the source of the EEG or the brainwave is, and that's neurophysiology. And this can be modeled as basically sort of coupling between the thalamus and the cortex at certain layers, right? And this, these sort of columns, right, that are oriented in the same direction, allow for the EMAG wave propagation to have lots of structure so that you can pick it up. And so the punchline is that depending upon what type of signal that I'm picking up, let's say it's a motor-related signal, then the average sort of oscillation range is going to be in the vicinity of a certain frequency band. Okay, so we can model this as something that looks like this. And then lastly, what we take advantage of is the fact that each one of those yellow dipoles, sort of what they represent, is going to covariate with what you're imagining because the brain has what's called a topographic map. And so what that means is that, for example, when I'm imagining squeezing my left hand, sort of which neurons are firing a lot and to the extent to which they are will be different than when, so you might imagine that some of those yellow guys on the right, were very active. When I'm imagining my right hand as compared to when I'm imagining my left hand, different guys are sort of active. So the high-level idea is that we just developed a very basic, state space model like this, and in this signal processing paper back in 2010, we got basically the best classification that existed for binary motor imagery. And the punchline is that a lot of people before were doing all this sophisticated machine learning, not trying to open up the hood and see what was underneath it. But if you do a sort of basic state space model, you can actually do very well. In fact, we did better than what the state of the art is. I haven't even followed what it is now. And you see the punchline is that we developed an asynchronous classifier where we don't make a decision until we're very, very confident about what's going on. So if the probability of left is, let's say, below 0.1 or above 0.9, that's only when I make the classification, which are where these red bars are. So you see that the time between these red bars can vary depending upon what takes place. So all I wanted to do was just give you a high-level explanation. Hopefully now you understand, based upon these basic sets of equations, how I can model this P of y given x. Okay? Details are not relevant. And so, but the punchline is that a lot of people have been spending time in the literature for the last few years is really trying to develop better P of y given x models, right? They're trying to get better, sort of Bayesian inference methodologies, and of course that is important. But we sort of had the epiphany that if we think about a brain-machine interface, it's just like when I'm working with my iPhone or even when I'm driving my car, and that is that this is not a one-step process, but rather this is a sequential process. And so the way I should really interpret a brain-machine interface is really two agents cooperating to achieve a common goal. What I mean by that is that when I'm driving my car, I can still operate my car even if I have a misalignment problem, right? And I can do that based upon the feedback the car is giving me. As the car starts to veer a little bit to the right, I turn the steering wheel to the left a little bit, I hit the accelerator, I hit the brake, etc., etc. The punchline is we really need this feedback loop. This is not a one-step process, right? Just like when I'm navigating on my iPhone, I don't zoom in on exactly the point I want just at once, but rather I pan to the left, I pan to the right, I zoom in, I zoom out. There's a sequential interaction between me and the iPhone. So we should really be thinking about a brain-machine interface along these lines. And so what you see in this picture right here, is this is sort of the way everybody was thinking about it before, but now note that we have indexed everything with the time axis, and note there's a feedback loop here, right? And so we really want to understand how should I think about this from a sequential process, really taking into consideration, in some sense, the $64,000 question is, what's the next piece of feedback that should be delivered to me, right? If I think about when I'm interacting with my iPhone, right, I fool around with my iPhone, then my iPhone shows something back to me. Based upon that, I then give it a subsequent command. Analogously, when I'm thinking about a brain-machine interface, or rather any human-computer interface, what I really care about is I'm going to provide some command to it. It's going to get a noisy version of that. It'll probably make some belief upon it was more likely you said one thing versus another. The first epiphany that we had at a high level is that rather than trying to spend a lot of time understanding about what the most recent command was, right? This is only the most recent time point in the past. What I should really be focusing attention upon is what is your high-level goal you're trying to accomplish, right? That's the belief I should really be maintaining, right? So the high-level idea is that there's two different types of signals, right? There's the high-level goal, which is where I want to get you on this map, the path I want to take to get home, etc., etc. This thing here is in some sense fixed. It's like a message point, okay? Exit time on is just the most recent command that I'm giving to the steering wheel, okay? It's going to get a noisy version of that, and then what's unclear to us up front is what is the next piece of visual feedback that I should give to the user. This is very, very unclear. So we could imagine, let's imagine just for the time being, let's think about the simplest scenario when there's no noise, okay? So let's imagine when there's no noise, I've got this Google Maps right here, I'm trying to zoom in on Champaign, Illinois, right? So let's imagine that the point I'm trying to interest, so let's imagine, just to make life easy, right? Let's imagine that I can only give one of four commands. I can just tell the iPhone what quadrant it's in. So I can tell it's in the northwest quadrant, the northeast, southwest, or southeast. So if it's in this particular quadrant, right, then what I will then do is I'll tell it, look, it's northeast. If there were no noise, what the system would do is it would eliminate all this stuff and just zoom in on this quadrant at the next point in time, right? That's what you would do if there were no noise. Now what if there's a little bit of noise, right? And the system has some belief, certain things are more likely than others, certain areas are more likely than others. What is the analogous effect of quote-unquote zooming in, right? We didn't know what that was up front. It was very unclear to us. So we want to explore this, right? So this is the high-level question we want to ask, is how do we optimally get the next visual display so that in the long run, the system is going to zoom in on a point on the map of interest as fast as possible, despite this being a sequence of noisy commands. So the first thing that we did is we always, I'm stupid, right? So I always rest upon the shoulder of giants, and I say, okay, well, what was, this is kind of a communication problem, right? I've got this message point of interest, and I've got a noisy channel, right? So what did Shannon tell me to do, right? Shannon told me that, in some sense, the right thing to think about is the mutual information, right? So we know that the normalized mutual information between the message point and the sequence of observations, right, is upper bounded by the capacity of this noisy channel right here. There's one point I'd like to emphasize, which I think is particularly relevant for these applications with humans in the loop, is note that I'm not treating the message as one of a finite number of hypotheses, the way we typically learn in information theory. Rather, I'm treating this as a point in a continuum. It turns out that you can still talk about fundamental limits, and you can reduce this back, right? But the starting point is W is really in a continuum, right? Okay, so what Shannon tells me, right, is that the punchline is that the next command that the user should give to the system should be statistically independent of everything the system has seen so far, right? That's really the punchline if you remember in your first semester of the information theory class, right? And if you think about 20 questions, you do that, right? 20 questions, right? If I'm picking a number between 1 and 20, and you query me, you don't ask me is a number less than or greater than 1, or less than or greater than 19. You ask me is it less than or greater than 10, right? And then I give you the response, right? At a high level, it's kind of, it's bisecting, right? But what's really underneath this, what generalizes to when there's noise, is the reason you're doing that is because the next thing I'm going to tell you is equally likely to be less than or greater than, irrespective of the command that I got. So it's statistically independent of what I've seen so far. So in some sense, you're handing me what's missing. And that's the right generalization, it turns out, right? Okay, so if I do a little bit of undergrad probability here, I can actually think this through for a second, right? And so let's imagine after one time step, the system has acquired this EEG signal, right? This noisy signal, and it's going to form a belief upon the message point. So it has some sort of belief or something like this, right? So now remember what I'm going to do is I'm going to take this map and I'm going to transform it to a subsequent map right here. That transformation is mediated by this map S. So S maps every possible point on this map to a point on that map, right? So if this map is smooth, and let's assume for the moment that it is, right? Then remember the probability of W lying in the vicinity of U is kind of sort of equivalent to the second guy, the second display being near S of U, all right? But if you remember from undergrad probability, we're changing the notion of length, so we have to weight it by the derivative of the transformation, or more generally, it's Jacobian, the determinant of the Jacobian. So this is undergrad probability, right? This happens always, right? What did Shannon tell me to do, right? Well, Shannon told me I better make sure that the next thing you tell me is independent of what I've seen so far. So this conditional belief should be the same as this unconditional belief, right? It's definition of statistical independence. Moreover, this should be time invariant, right? If this channel always has the same statistics, there's a unique optimal statistical law, right? Also remember from first semester. So the punchline then becomes this equation right here. It's this Jacobian equation, which is that I'm indirectly describing the map, the optimal way to map from one display to another. I'm not explicitly telling it to you, but more I'm telling you to better satisfy this equation, right? This is an if and only if condition, right? So far, so good, right? So everyone's with me to high level, just undergrad probability. So what's interesting about this is if you look this up, this Jacobian equation, this is everywhere. This is in fluid mechanics. This is in blah, blah, blah. So this really got us scratching our heads, right? And so the first thing I can do is let's take a look at this narrow. The message is just a point on the 0, 1 line, right? So let's imagine that it's just some point on the 0, 1 line. Well, the first thing that we can show is that there are a lot of other results in the information theory literature that have thought about communication of a message point in a continuum. They've all sort of thought about it being on the 0, 1 line. It goes back to originally the binary symmetric channel by Horstein. Then Stolzwith and Kailoff won the Best Paper Award in '66 for looking at the Gaussian noise channel. And then more recently, Shavitz and Fader wrote this really beautiful paper, really generalizing all this stuff for the 0, 1 line, right? So anything for the 0, 1 line can be captured in this notion of posterior matching. So what I would like to do is just show you how the posterior matching is nothing but the Jacobian equation when we have the 0, 1 line. But it's very simple, right? So remember, for the 0, 1 line, what's the most natural optimal input? It's not surprising. It's uniformly distributed, right? So if this guy is uniformly distributed, right, then no matter what point you're at, right, it's uniform, right? So the height of this density is just 1, okay? Moreover, this thing is just in one dimension, so the Jacobian is just going to become the derivative of the map. Let me assume the map is increasing so I don't have to worry about the absolute value. And look at what I'm saying right here. The map better have the property that its derivative at W is equal to the density at that point. And that's kind of sort of obvious if you think about it, right? Because what that's saying is I should be zooming in a lot where I'm very confident, right? So what that means is that wherever the posterior belief is high, I should be zooming in a lot there, right? That's the high level idea. So what if I take the integral of both sides? So back up here, derivative, right? Here this, I'm just going to integrate both sides. And what do I get? I get that SYW, that was the posterior density. Now this is the posterior cumulative distribution function. So this is what Shavitz and Fader did in their paper, right? So what we're showing is that the Jacobian equation and posterior matching are the same thing on the 0, 1 line. Okay? So now with the 0, 1 line, let's see what we can do in terms of having some fun. Right? So let's think about a brain-machine interface application where the message point is on the 0, 1 line, right? So let's first think about spelling a sentence, right? Sort of noisily, right? So here's the basic setup, right? So what I have here is the 0, 1 line, okay? And I'm going to think about spelling a long sentence, right? And so if any of you guys are familiar with Dasher, this kind of feels like Dasher, but now this is Dasher when it's noisy, right? Okay? So if you don't know what Dasher is, put your earmuffs on. So this represents the point 0, this represents the point 1. So the first thing that I do is I use an arithmetic code to try to map every possible infinitely long sentence to a point on the 0, 1 line. And if you fool around with it, you kind of get the idea. The first thing I do is let me take a look at all sentences where the first character is A. That corresponds to this interval. All sentences where the first character is B corresponds to this interval. Here is T. So the sentence I'm trying to spell is the black cat jumped over the lazy dog, okay? So these are all the sentences where the first character is T. Now, and notice, by the way, that T has a very long length. Why? Because T is very likely in the English language. So I use the arithmetic code so that things that have higher probability are longer. Okay? So what about sentences that start with T and H, that begin with T and H? That corresponds to this sub-interval, right? That kind of makes sense, right? This could be like TA, TE, this is TH. So you start to see what's going on here. So what I do is I say, well, look, I'm trying to spell the sentence, the black cat jumped over the lazy dog. So we did this with a real brain-machine interface where a guy is imagining his left hand or imagining his right hand. So in this scenario, he imagines squeezing his right hand, okay? The system is going to get that EEG, it's going to form a belief over all possible sentences based upon what he said, and it's going to crank out that posterior matching scheme, and it's going to redraw everything. And this is what it looks like, right? And what you see, what's kind of cool is it's kind of sort of begun to zoom in on a number of stuff, including T, and it's zoomed out a lot on stuff over there. So you're zooming in on what's important, you're zooming out on what's not important. Note that because there's noise, you never want to completely eliminate anything because, you know, there's noise, but you just want to have the effect that you're zooming in more on stuff that you're more confident about. So here in this scenario, I'll say, look, I care about the black cat, so now I'll say right again, and it'll show me this. And notice now how I've really begun to zoom in into T. T and H are really starting to show up, in particular THE, right? And the software underneath how we did this, we had a smart computer science kid do this. And so Raheem in the audience knows this because he was an undergrad at Illinois when he worked in there. And Cyrus Omar, who's now a grad student at Carnegie Mellon, coded up all the software underneath this. Detail not relevant. But you guys kind of see the idea so far in one dimension. And so now I can give you another scenario in one dimension. It turns out you can do a lot in one dimension, so let me show you here. So now we want to do something more ambitious, and we want to try to do something crazy like flying an airplane over the cornfields of Illinois, only with your brainwaves, right? So the first thing we thought about doing is, let's think about a path that we're trying to specify. So in this scenario, the key thing, the key message point or whatever, right, which is a point on the 0, 1 line, what I'm going to do is I'm going to use a different type of arithmetic code. And now what I'm going to do is I'm going to, basically what I do is I take a smooth path. I represent a smooth path as a bunch of infinitesimally small arc lengths, right? And then I just create an ordering for the arc lengths, right? And in particular, very, very counterclockwise is the smallest, and very, very, very clockwise is the biggest. Once I have an ordering over a discrete alphabet, I can create an arithmetic code. And so what you see in this example is that here's the point 0, and 0 corresponds to a very aggressive bank counterclockwise, 1 corresponds to a very aggressive bank clockwise, 1/2 is sort of going straight up, right? And what's nice about this is we sort of have this translation between the language in which the computer speaks and the language in which the human speaks. Computers like thinking about zeros and ones, and so this is like the belief that it's formed, but humans like smooth stuff, right? So I'm only going to show smooth stuff to the human, but underneath the hood, I'm going to be maintaining all these beliefs about stuff on 0, 1, and this is the translation. So the high-level idea that we perform here, we can show that this is optimal, is that there's only one piece of feedback you need to give to the user. And that ends up being what's called the median of the posterior belief. And that's the point where half the probability is to the left, half the probability is to the right. So I look up where the median of the belief is. So if I integrate under this curve, I get 1/2 to the left, and likewise to the right. I take a look, where is this on my arithmetic code, and I draw that on the screen, okay? So what this gray path is, this is what's in the user's head. This is W that's in their user's head. The computer doesn't know that. And at every time step, all the computer is going to do is going to update its belief, find the median, look it up in this table, and show it on the screen. And now the only thing that the human has to do moving forward is, remember, he has to say, 0 or 1, imagine left or imagine right. What is the rule? Well, the rule is very simple. All he does is he looks at the first location where the two paths differ. If it's a clockwise orientation, that means imagine squeezing your right hand. If it's counterclockwise, that means imagine squeezing your left hand. And so that's all you have to do, and you can see that it works. So this is data taken from a real EEG experiment with Ray's brain here. Okay, so this gray one we're just overlaying for the purpose of, for visualization for you all. The only thing that's being shown to him on the screen is this path that's partially black and partially red. And note that because there's noise, right, as I said before, in one shot, it's not going to be able to find exactly that path. But note that what it is doing is it's sort of sequentially removing uncertainty, and that belief is becoming to get sharper and sharper and sharper and narrow, and it's converging to basically a point mass, a delta function centered right at the message point. And what you see is that this path, the beginning parts of the path have lined up on it, and sequentially with time, more and more of the latter parts are. And the reason I show part of it black and part of it is red is just to show that the stuff that's black means that that subpath I'm extremely confident about. It's greater than 99% probability. Yeah, that's, I forget what the numbers are. Again, it's done in software. But you sort of see the punchline, right? You see that more and more is beginning to line up, more and more of the subpath is lining up with the true one, and it's just eliminating more uncertainty sort of moving forward. And this is what the noisy signal, this is all with brain control, just imagine left, imagine right. So then we went one step further. We collaborated with an aerospace engineering professor at the University of Illinois. We got a remote control airplane, and we gave it a motion planning algorithm. So we basically took this system, right, shoved it into a motion planning algorithm, and flew an airplane over the cornfields of Illinois. And hopefully you see why this works. Why it has the potential of working is because, remember, the nature of the scheme is such that the subpaths early on are being zoomed in on with very, very high confidence, and it's just the latter parts, right? That's perfect for any type of system that has real kinematics because the plane has to be here before it's over there. So as the plane is flying here, it's very confident about, you're specifying the uncertainty about more further out. So it's always, so it works, right? And so here's sort of a picture of the path specified by the user is the one that's blue that has little white dots on it, and the other blue one is the one that the plane really flew. So the punchline is just that this sort of stuff works. So am I suggesting that our Delta airline pilots in the future are going to be doing this? No, but I on purpose wanted to be provocative to demonstrate that the importance of using feedback, right? And if you use it the right way, you can do much more sophisticated stuff than you thought otherwise. Oh yeah, go ahead.
So does it matter what, if they imagine the word left instead of visualizing the plane turning left, does it still work? Or? That's
a good question. So it really depends upon what aspect of the brain signal we're trying to pick up. So in this scenario, so remember we have that noisy channel? That P of, it needs to be the case that the statistics of the neural signals that we're getting reflect the P of Y given X model that we have. In our scenario, we're really picking up on the motor aspects of the brain, so we really need you to be sort of doing something that involves motor imagery, right? That being said, if we wanted to do something else, we could just change our algorithm accordingly. But in order to get this to work, one area where you really do need understanding of the brain is your P of Y given X needs to be indicative of the statistics of what you're requiring. So the motor imagery, imagining left hand, imagining right hand, sort of has to work, right? Right. Yes, sir.
So I'm just curious, would it work without feedback? I mean,
basically no. And the reason is because you're going to need forward error correction if you don't have feedback, right? If you want to have reliable communication, right? One beauty about feedback is that you can basically just sequentially hand the errors, right? When you have even across a noisy channel, right? If the right piece of feedback is being given to you, you can prove that you can have reliable communication and zoom in. If I want to exactly zoom in on this message point and I don't have feedback, I'm going to need some notion of forward error correction. And I imagine that's gonna be very complicated when we have a human user in the loop,
So
right?
if you show the code board to the human,
He's gonna have to remember the whole sequence.
yeah, but you
Right.
can
You need a
In
trophy.
principle, but I wanna, remember the punchlines, I really wanna make this as easy as possible for the user, right? Think from a Steve Jobs perspective, right? From a form factor perspective, I want it to be minimal amount of stuff the human has to remember, has to do, right? So the feedback really, really helps you in doing things. It's the reason driving your car works, right? Just look at what's going on, you look where you wanna be, and you just turn to the left or you turn to the right. So feedback really, really reduces complexity, right?
So it's actually, so the feedback helps in terms of delay as well, I guess, because.
There's other aspects, and then some people bring it up, but I don't think that's relevant for these applications. I think what's really relevant, if you have any application where it's easy for the human and it zooms in, I think it's a win, right? I think if the error exponent is bigger or smaller, I think those are important for communications applications, but I think if you can build a system that robustly kind of zooms in, right, when stuff is noisy and it's easy for the human to use, you know, everybody in Silicon Valley is already happy, right? Yeah, yes, ma'am.
When you have enough feedback, can you do learning so that you can forward correct eventually?
Are you saying indirectly through the computer?
Yeah.
Absolutely. So in fact, we do that. So I'm not going into the details, but we actually do learn because another thing that I'm not talking about is the brain is inherently plastic, right? So even as the human is interacting with this, he's kind of learning how the system is interpreting him and how he wants to. So his brain is actually changing in the process. So then what we can do is we can do co-adaptation, and our computer can be learning how his brain is learning, right? And so we do some of that, but you have to be very careful, right? We have co-adaptive systems, you can, right, but we do that. We have a protocol where after a certain number of trials, we blah, 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 blah. But those are sort of details. I want to just kind of give the higher level picture, but those are great details. Yes, sir.
How is that, this is for sure related, I guess, but how is that related to, there's a field in machine learning known as active learning.
This is exactly active learning. This is exactly active learning. And so in fact, if I get a moment afterwards, I can show you that the Porstein scheme, 1963, is exactly a certain instance of active learning. I don't know if you've seen these scenarios where you're trying to minimize a convex function, right? And then, so you have a convex function, right? This black box is going to spit out to you the derivative of the function at some point, and you hear it through a noisy channel. And then just like how the computer gives the feedback, the key thing you get to do is you get to query it. You know what? I want to now ask you what's the derivative at this point. What I can show you is that for the function y equals the absolute value of x, the optimal thing to do is exactly the Porstein scheme. Right? Because if you think about the derivative is going to be +1 or -1. That's kind of like the input to a binary symmetric channel, right? So for one specific convex function, namely absolute value of x minus the center point, Porstein, right, is exactly that problem. So some of my friends, a guy named Maxim Roginski, who's at University of Illinois now, he and another guy named Sasha, I forget the guy's last name, but he's at UPenn, Wharton's at UPenn, right? He's at Wharton Statistics, and they've written a number of papers kind of showcasing this relationship between feedback information here and active learning. So they're fundamentally related. Because again, the feedback loop. Does someone else have a question? Yes, sir.
I just want to ask, what's the bit rates? Like, how fast can I calculate 1 to 2?
So remember, all I need to know is the capacity of that noisy channel, right? So second, you have the capacity of that noisy channel. This scheme that I'm talking about provably achieves capacity, right? So Shayevitz and Fader, posterior matching, that scheme achieves capacity. So all you have to do is find the capacity of that binary channel.
So what's the capacity?
I forget what the numbers are. And the reason I forget, and maybe this is from my perspective, I think this is a huge leap, right? Where now I can zoom in on something with feedback, with a human doing something very, very simple. Before that, you couldn't do it. I feel like that's a big conceptual value add, trying to dictate the details of the notion of capacity. I'm not, maybe irrelevant, maybe or not, right? We have it in our paper, I could look it up. I think it's approximately 70 bits per minute, somewhere around there, so about 70 bits per minute. Right? We have to define bits per second appropriately, and so what you have to do is, remember we have an asynchronous classifier, right? So what you have to do is the denominator needs to be the average amount of time it takes to classify, right? It's without sampling, right? It's asynchronous, right? And the numerator, you have to talk about reliable bits. So there's a framework to do it. And if I remember correctly, it's around 70 bits per minute or something like that. Yeah. So now, let's go one step forward. So remember originally, what did I want to do? I wanted to zoom in on a point on a map, right? That's what I really wanted to do. So far, we haven't done that. A map is in 2D, right? So this is where things really get interesting, right? We have to develop new information here. So I thought this was cool, right? So far what we were able to do was we were able to walk on the shoulder of giants, you know, Horstein, Kailash, Stoltwith, Shavitz, and Fader. But then what we were really interested in is this problem right here, right? Zooming in on a point on the map. That's a point in 2 dimensions, right? So now what we need to do is we need to develop new theory, it turns out. And so the punchline is that the Jacobian equation is still going to hold, right? This equation holds, this statement about densities, right? This statement holds in an arbitrary dimension, right? But what's unclear is how do I construct a map that satisfies this equation? If we were in 1D, we were just talking about the derivative of the map, we could integrate both sides, right? So that problem is very, very hard. And it turns out it goes all the way back to the 1600s. Trying to find a map that satisfies this equation is very, very, very hard, right? It's non-convex, blah, 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 blah. And so a guy named Kontarovich won the Nobel Prize in the 1970s for basically nailing problems that look like this, right? The connection to feedback information theory obviously was not there, but the high-level idea is if you think about what is any map doing, right? W has statistics on her, right? The map is moving W1 to W2. That's really inducing a joint distribution on W1 and W2. A joint distribution on this guy and this guy, right? So let me first try to optimize overall joint distributions, right? And see what happens, right? And so the punchline is now I search over the space of all joint distributions, right? And what do I want? I want to guarantee that if I marginalize in 1 dimension, I have my belief, right? My posterior belief, right? The information that really I had at time step 1. And then what do I also want to do? I want to guarantee that 1 time step forward, the next thing you tell me is statistically independent of everything I did so far. In general, that equation, I'm marginalizing out W1, it's always going to be this distribution, but remember, Shannon told me that I want this guy to be independent. So that should be equal to just this guy here. So now let me take a look at the space of all joint distributions for which these constraints hold. Note this is linear, right? This is linear, this is integral, right? Linear constraints, it's convex, this is beautiful. And now let me do the following, right? Let me search over all joint distributions. Let me minimize some cost function, right? Let me just see what happens, right? So it turns out if you pick the right type of cost function, maybe like a Euclidean distance, what you can show is that the optimal distribution always is going to pertain to a deterministic map. It's really cool. So that means if I run this algorithm, right, which is a linear program, if I use the right cost function, I guarantee that I'm going to get a map that I want. So we do that. And so moreover, there's a lot of people, once you now have mapped this to the optimal mass transfer problem, there are efficient algorithms to do this. And in particular, this guy Tannenbaum, this stuff is used all the time in image registration, right? And many other literatures, right? So there are existing efficient numerical methods now to find this map after we make the connection to the theory of optimal transportation. So we also went 1 step further when we said, well, look, maximizing mutual information is necessary but not sufficient to achieve capacity, right? We know it's a necessary condition, right? But there exist scenarios where you maximize mutual information, right? But you're not achievable, right? So what we also began to do, and this was really mediated by the fact that W is a point in a continuum, we were able to make a fundamental relationship between reliable feedback communication and the stability of the nonlinear filter. Namely, the stability of Bayes' rule when you're dealing with the hidden Markov model. So this is recent stuff that Ramon Manhandle at Princeton has developed. Okay? And the high-level idea is actually quite simple, right? What does it mean for reliability from 30,000 feet, right? Well, that means that when I get all my observations, what should happen? I basically should have W, right? So I can take a look at the sigma algebra generated by all my observations, compare that to the sigma algebra generated by all my observations and the message point. If these two are the same thing, that means I've zoomed in on W, right? If they're not, I haven't. It's yes or no, right? So basically asking this question and exploiting the Jacobian equation, you end up with a necessary and sufficient condition that also appears in the stability of nonlinear filter. So basically what that means is that when we're dealing with this message point notions of reliable communication, it's basically the same question as what you find in the question of filter stability. And the punchline here is it's just like leverage. I'm not going to go into the details of all this stuff, but the high-level idea is that I'm just piggybacking off stuff that already exists, show these two things are the same thing, and then just invoke all their framework. Yes, sir?
So what metric could you use to determine if those 2 sigma algorithms, the randomness in those 2 sigma algorithms is approximately equal?
Right, it's a great question. So basically what we really do here is we have to make sure these two things are the same, P almost true, right? So there's some probability measure governing everything.
Yeah.
As long as these two are equivalent P almost surely, then we're happy, right?
But you could also just have some sort of monotone function for difference or something like that that would
Right, so what you could do is you can take a look at a conditional expectation of some random variable, given this sigma algebra, compare it to the conditional expectation of a random variable given
Not
that
one,
sigma
you have
algebra.
to look at all,
Say it again.
not one of them.
Or, no, I'm sorry, a random variable given this, yeah, exactly. You have to search over a large space of such random variables, right? You have a large enough space, and that basically is equivalent to this, right? But the punchline is that there exists known machinery to asking these types of questions, right? There's a known machinery in probability theory to ask these types of questions, right? So I don't want to go into too much of the details of that. I just thought that it's interesting that when we think of this message point framework, we now develop new connections to other fields and apply probability. So now we can do fun things like zooming in on a map, what I originally wanted to do. And so here's a scenario where I'm trying to zoom in on this picture of Shannon, right? Playing with his little mouse. You guys are probably familiar with this picture. Okay, so in this scenario, I've got this, 2 dimensions, and this is the point that I care about. I'm going to zoom in on his chin right here. So in this scenario, I'm going to say, I'm going to punch him in the chin. So in this scenario, I've got 4 quadrants, northwest, northeast, southwest, southeast. So I'm going to tell the system northeast, right? The system's going to get a noisy version of that. It's going to update its belief, and now it's going to crank out that optimal transportation problem, and it wants to reshow the picture. And the key thing we want to see is what happens when it reshows the picture. Does it have the effect of zooming in? And the answer is yes, right? So just to back up for a second, this is where we were originally. Now after one time step, it looks like that. So you see how his head got bigger and his hand got smaller. So it kind of has the effect, right? We're zooming in. Now we do this one time step again. So now I'll say southeast, right? It'll hear it through a noisy channel, update its belief, do the unicorn algorithm, right? And then we do that. And zooming in again. So we went from here to here. So you sort of see how this works. And we can do this over and over again, and it's eventually going to zoom in right on this point of interest, even when there's noise, right? So, so the high level, so this begins to allude to, so how much time do I have, by the way? Someone, anyone?
15 minutes.
Okay, so now what I'll do for the remainder of the talk is, so hopefully what you guys sort of appreciate right now is that there's been this very fun interplay between, look, I want to solve this brain-machine interface problem, I have to think about it the right way, the message had to be a point on a continuum, right? Leverage this other machinery, right? But I only want 2 dimensions, so you got to develop new theory, optimal transportation A, and then B, the relationship with the nonlinear filter to guarantee actual reliability. So you sort of new theories coming out of this application, and then you turn around and you solve the application, right? We originally wanted to zoom in, we've accomplished zooming in. So, so this slide here represents the Economist, and now they've sort of begun to get interested in this. And they had this article in September 2011 talking about things that used to be hoaxes in science fiction are now fast becoming a reality. But one thing you might not like about this talk, or this slide, is the picture, right? The picture is not cool, Steve Jobs not happy, right? So one of the things that we subsequently did as we started to get brain-machine interfaces to work is we began to ask the question, what if I could really make these things ubiquitous and useful in everyday lives? Drilling people up with these caps is not going to be the answer, right? This is going to keep us in the laboratory only, right? So then we asked ourselves, okay, well, what if I only care about monitoring stuff on the forehead, right? It's not much better, right? You'll get teased if you walk around campus with that on. Analogously, if we care about skin-mounted technologies more generally, with a picture like that, bricks on straps. And so the reason is actually quite fundamental. It's because biology is soft, curvilinear, and elastic, whereas the building blocks of electronic circuits or semiconductor wafers, these things are flat, rigid, and planar, right? You couldn't have a larger distinction. So what we did at the University of Illinois is collaborate with a material science professor. It turns out that you can develop tricks where you can peel off a thin layer of silicon, and even silicon, right? If you make anything thin enough, it's bendable. Even silicon, it's got a thin layer of doped silicon. You mount this onto your favorite biologically inert stretchable material, and now you can accomplish stretchable electronics. And so what we attempted to do with this was to do something kind of crazy and radical, but let's see if I can now monitor your brain signals by just slapping something on your forehead. I want to be extremely thin, extremely light, very, very bendable, right? And I want the electronics to be robust to mechanical deformations, and it turns out that we were able to accomplish this, and Raid in the audience is actually a co-author on this paper, so he helped us with this project. And so basically what we call it is electronic temporary tattoo. Here's a picture of the device naturally. Here it is in its undeformed state, and it's bound so close to the skin through the forces of atomic interaction that when you compress the skin or when you stretch it, the device will stretch naturally with it. Moreover, you can embed the device within a temporary tattoo. Okay, and so you can have, pardon me?
I said,
Yeah, and so what you can see here is the electronics are actually inside right here, and the system bends naturally with the skin. Okay, and here's a blow-up picture of what the device looks like. You can see the skin here in the background, and the device is multifunctional. It has an oscillator and an antenna for the basics of wireless communication. You can actually do inductive coupling to deliver power to the device wirelessly. It has an LED for status indication, and a variety of bodily signal acquisition modalities like EKG or brainwave or et cetera, et cetera. So remember, the thing that we were really after was checking to see could we actually pick up EEG. And you know, the EEG, the brainwave, is a very, very small signal. It's about 1,000,000 times smaller than the voltage across a AA battery. It's in the microvolts, okay? So it was unclear if we were able to accomplish this, and that was actually my real goal, but luckily we were. And so this picture, what you see is, what you see right here is it's well known that when your eyes are closed, there's an increase in your alpha rhythms because you're not paying as much attention, right? So you can see an increase in alpha when your eyes are closed as compared to open. And when your eyes open and blink, that's a very fast response in the time domain, right? So it spreads everywhere in the frequency domain. So you can see it spreading everywhere here. And here's another more recent picture in a collaboration with a neurologist showing that we're picking up brainwaves from it. So we have some challenges in this device that I think might be interesting for the science and information community more generally. And the main challenge is that we have to think about how to design these systems so that they're robust to mechanical deformations. And so, like, for example, it took us 3 years to get this project to work. We didn't pull this off overnight. And one of the reasons it took us 3 years is because you have fundamental material science, fundamental biology, bioengineering kind of stuff, you know, neuroscience, and also fundamental mechanics, right? Because you have to really guarantee that this system is going to work across the natural bodily deformations. And so typically, we as double E's, primarily in the audience, we don't pay attention to mechanics, right? We're assuming it's on some wafer, everything is fixed and planar. The way we learn circuits, the way we learn all of these things, we don't pay attention to, for example, how the fact that an inductance is going to change as I stretch an inductor, right? Et cetera, et cetera. So one of the things that we really need to rethink are how we design electronics for bio-integrated systems that are robust to mechanical deformations. And I think that this is a challenge, you know, to all of us. And for example, imagine what if we could map what took us 3 years into 3 months. Imagine what the implications could be for all of us, right? And so I'll just give you one example of this, right? This was in the supporting materials paper, right? So this is not in the main document. You have to go online to find this. Not everything works, right? So we demonstrated we had an oscillator and an antenna, but not everything works. And so, for example, if I take this oscillator, right, an inductor and a capacitor, and I only stretch it a little bit, right, the carrier frequency changes. It's not surprising, right? It's an inductor, and I'm stretching it, right? It's not rocket science, right? So this led to us more recently developing a new approach, right, to thinking about a wireless communication system that is robust to mechanical deformations, that does not have that fragility. And I'll just show you the picture to show that it works, right? So here's the original EKG signal recorded right here on your skin, and here is what we sort of wirelessly transmitted and decoded, and the punchline is that you're still picking up the bio signal, right? So the punchline is that in order to get this to work, this was not just a, you know, bits over a noisy channel sort of thing. We have to really go back to the physics and think about the electronics. If we think about science of information, how it connects to biology and other disciplines, we're not going to be able to completely abstract all the other things and keep them as constant. Everything kind of folds and changes together. So it's an interesting challenge, and it's going to be a fun direction for the future. And I think I'm almost out of time. Let me know how much time I have. So anyone, am I out of time?
2-3 minutes.
Okay, I'm just going to shut up now. So we got many applications of this technology. One of which is we can replace an EGCAP with just a forehead monitor signal. We can pick up the same brain signal, right? So what we show here is basically, you know, all the polarity is swapped. That's just a notion of what we call plus and what we call minus. We can pick up the AHA cognitive brain signal, typically done with a complete EGCAP. We can now do it only with the forehead monitored acquisition device. So those are just submitted to the Society for Neuroscience Annual Conference. And you can imagine that once we make this wireless protocol integrated to perhaps map to your cell phone, we can begin to explore what some of the potential applications can be. And so I will shut up from there and just say that one last thing I'll say before I conclude is that we're also actively involved with the clinicians at UCSD. And so one of the things that we're doing is really exploring sort of preterm birth from before the baby is delivered as well as afterwards. And so, for example, we'd like to replace, anyone here who's had a child knows that this is a big pain in the butt when you're in labor and they put this, the fetal EKG monitor and you have to be in just the right place, et cetera, et cetera. Imagine we could replace that with just this tattoo, and this could acquire a variety of vital signals from both the mom and the baby in a much more, comfortable form factor. Or if the baby unfortunately is born prematurely, right? Imagine if the mom and father really want to have that close skin contact with the baby as he's young. Right now, this is what it looks like when they're doing monitoring of the brain of the baby if he is born prematurely, because they have to monitor for seizures and other things. Imagine instead if we just had the tattoo. So these are some of the projects that we're working on to do translations to try to get this in the hands of many people. So that is all I have to say. So how I would like to conclude is, if we remember this picture right here, right? We talked about the applications of this, et cetera, et cetera. We didn't like this picture. Imagine if this instead was the picture that was in the Economist, how people might be able to use their imagination on what we could do with this. And so, with that, shut up.
Any questions?
So are these energy harvesting devices?
It's a great question. So I didn't go into that, but we do have, so another $64,000 question is, how are you going to power the device? So what I demonstrated right here is that we can do inductive coupling, right? So we can do RF inductive coupling, but we're also working on far field inductive coupling. There's many ways that you can do inductive coupling. Also, there are new technologies that are being developed, extremely thin, flexible lithium-ion batteries. So the same types of batteries that are elsewhere, they're becoming thin enough that they could actually fit within like a 50 micron thickness and be bendable. So we're exploring a variety of techniques, one which are very conservative, lithium-ion battery, inductive coupling, but we're also thinking more fringe and really trying to blur the distinction between what's biological and what's not. And so something else we're thinking about is actually picking up off the kinetic energy in your body itself. So as you're always active, right, that kinetic energy, we might be able to transform and store energy onto the device if we have something called piezoelectric material that changes kinematic energy into electrical energy. And there's a recent result that just got featured in Technology Review. It's a guy out of Korea who's got some really wild stuff where he can pick up quite a bit of energy right from just your body's kinematics. So I think because of all of the energy, or all the energy, quote unquote, that's being devoted to the energy problem, we're not as worried about that. Yes, sir.
All of this stuff works at wavelengths that's not going to cause cancer.
Right. So for example, remember I showed you a certain amount of gigahertz, right? That's the same gigahertz band there, cell phones and whatnot, right? Moreover, the amount of energy that this is going to radiate. So, I guess the idea that we have is that we don't want this thing to have a cell phone transponder on it. Rather, we want this tattoo to just transmit to your smartphone, and then your smartphone uploads to the cloud. So all we need is enough juice to kick this to your smartphone. I don't want to have the same type of, because this is too complicated of a circuit anyway, right? Remember, less is more in these applications. So our model is to radiate much less energy, a simple, robust way that's robust to mechanical deformations to get the bodily signals off the device and onto your smartphone. So as such, there'll be much less